We don't know everything.
These guys here, they were thinking we'd be looking at telescopes or at the Milky Way or at least a star, but we're not. We're looking at the blinding lights instead, but we're at night.
Okay.
We can't win them all. We didn't order that cloud, but it's there. So these guys are going to do something good. He does this thing, all right? And evidently it's his best known.
Don't give it away.
This is going to be good. For a filler, this is good filler, I guess. But we're going to, I want to make a quick announcement before I pass the mic to Judith. She's going to get us started. We have Nate Wood here that just arrived. Nate, are you out there? I think, there he is right there. So Nate's got 2 night vision goggles, and we've worked out a deal where, people can use these things. They don't work good, just like the telescopes that for looking at the night sky. So you can't see through the cloud. But if the cloud breaks after this thing, he's got the night vision goggles. They're very sensitive to light, so we'd have to go to the Singularity site just across the way. But we may have a little bit of night vision goggle action later. And with that said, please welcome to the stage Judith Jubb.
Hi, thank you very much. I grew up in Colorado, and I'm very familiar with these mountains and road horses, and even in my youth was a rodeo queen. So I really have a rapport with Carrie King and what happened to Snippy. A question always comes to my mind, and that is, what's going on? I mean, why are these people doing this? Anyway, so that's what comes to my mind. What is going on? Why is this happening? And they're not really mutilations in the sense that they're very surgically done. They're very, very accurately, specifically.
I think she needs it.
Operations. But it's so very strange. I'm here tonight. I'm over here from Pagosa Springs all summer long at Chimney Rock National Monument. I show constellations of the stars. But since we can't do that tonight, I always bring with me star maps. And I printed up 50 because last year when I was over here, that's about all the people we had. We even had some left over. So this is just every month, the star constellations that we're looking at changed because as we orbit around the sun, we're seen in a different part of the universe, of the galaxy. So every morning, the sun rises. That's the center of our solar system. And we see that. But during the nighttime, in our orbit around, through the seasons, then we see something different. So I want to demonstrate this a little bit, and I'll pass it around. And I'd like you people to take them, but be sure to share because I don't have enough for everybody. Of course, we had some people that had already decided they're going. But let me show you how to do this. This looks like it's quadrant foil. So north, east, south, and west for the month of the end of August and through the first part of September.
It's free.
Oh, thank you. And so what you do, this is the overhead point right here in the center. So you hold your map up, and you see right now the constellation Lyra is almost right over us. And Vega in Lyra used to be millions, hundreds, thousands of years ago. Lyra was the North Star, was Polaris. But because of the shift and the way we're traveling through the universe, now we have a different Polaris. We have a different North Star center, and that happens to be in Ursa Minor. So these are the major constellations. And the best time to do this is in the twilight, because that's when the biggest stars, the most important stars for human beings for thousands and thousands of years, is when they pick out the bright red giants in Scorpio and the bright red giant in Boötes. And so what you do is you just decide when you're looking east, down on this is the horizon. These tiny little houses that are on the wings of every one of these, that's the horizon. And then the overhead point is right in the middle. And these are all the major constellations. Now, this is the same system that is used by NASA. And it could be Chinese system or Native American system. We all have different constellation stories. And the reason the stories are here with these constellations is to help people remember. It's a mind trick that people do to remember by association. And they would know that that's right, that's the big bear, or that's right, that's going to be, and this is what we do. So right now, James Webb Telescope is focused on the southern hemisphere constellations and nebula that we can't see from here. The only constellation we can really see is Pegasus, and you have to look for certain times of the day and night. And right now, if you go out before dawn, there's been this wonderful, all the month of August, there's been this wonderful interplay with the moon and with Venus and Jupiter and Mars. And you can actually see these just with your eyes. You don't need a telescope or binoculars. I frequently use binoculars. That's how I learned with my dad. My dad was a naval officer, and at the academy he had to learn how to navigate through constellations. So this is a very old system. And some of the names of these stars come from Arabia because of all the camel caravans that would go through. And how could they tell? I mean, there it is, desert for miles and miles. How are you going to tell where you are? How are you going to tell where you should be going? Because of the time of the year, the stars in the sky, and it points you in the right direction. So I do have a little script that goes along. So you get 2 pages, and this tells you a little bit about the north constellations, the east, the south, and the west constellations. We're so fortunate to be in this dark sky area when we don't have clouds that we have perfect viewing time. But the sky is so clear, especially in the winter in Colorado. It's cold, but you see so many stars that sometimes the constellations are hard to pick out. So that's why I suggest we do it in twilight when just the biggest stars are visible. And in that time, too, after the sun has set, you can see the color in the stars. And the colors in the stars, one basic aspect is the chemicals, the elements. And the oxygen burns blue, hydrogen burns yellow. Our sun is a yellow star. And these are the most common stars. These are middle-aged and not baby stars, and they're not aging red stars, red giants. But it's really wonderful, and I've done this all my life. I love the stars. And Marc will probably tell you more about it, but we have these little headlamps for red light because it's hard for the contrast if you have a white flashlight or something and then try to look up in the stars. So that's what I'm here for tonight. And then tomorrow, bright and early at 9 o'clock, I'm going to be talking about some of my clients. I didn't start out being a UFO or MUFON person, but my husband was an Air Force pilot and ended up at Area 51 when he was promoted and did a lot with the inventory there for several years. But in his retirement, he went around the world looking at crop circles, looking at evidence And so much of this has just come out recently, but it has taken years and years of mutilations, of crop circles, of all these other phenomena. We are a part of this universe. We are part of this galaxy. We have never been on our own here. And I feel very comfortable talking about the stars in this galaxy. These constellations belong to Earth. If you went someplace else in the galaxy, you would have different constellation. This goes into astrophysics and a whole bunch of stuff. But these constellations, Leo Major, Leo Minor, Ursa Major, Ursa Minor, you have a big bear and a little bear, a big lion and a little lion, a big dog and a little dog. They belong to us. This is where we are in the galaxy. This is who we are. We are Earth. We are of this planet and our makeup and everything else. So I will pass these around, but like I say, I didn't bring enough for everybody. And so if you're a member of a family, maybe you could just take one and maybe make your own copies. And tomorrow morning, I hope to see you because I'll be talking about people that have come to me sharing these stories of their UFO contact, abductees, but we also have telepaths and clairvoyants that have been receiving messages for years, hundreds of years that I know of, in waves. And it's important that we know these are real. Clairvoyance is a science. It's not just hocus pocus. There's energy waves that have color, that have sound, and some people are particularly sensitive to these things. So just because this person tells us something we can't see or that we don't hear doesn't mean it isn't there. Somebody is hearing these things. Somebody is getting information from extraterrestrials. And I'll be talking about that tomorrow morning at 9 o'clock at Sand Dunes. So thank you very much.
Good. Yeah, I'm okay. Yeah, go ahead.
Am I supposed to introduce you?
No, I can do that. That's okay. Hi, everybody. How you doing? My name is Marc D'Antonio. I'm an astronomer. This is what we look like. Not exactly. I mean, sometimes you wear a coat and a tie. Sometimes you're basically grumpy and your hair is disheveled. Your glasses are like this, and you just woke up because you're going to go use the observatory late in the morning, like 3 a.m. or 4 a.m. Done that for many years. And I think there's an audience here. I can't see you yet because I'm not quite awake, but I think you're here. I heard somebody laughing about it before. Anyway, you know, what Judith was talking about was wonderful, and she talks about some of the folklore. She talks about the great bear, the little bear, Ursa Major, Ursa Minor. And, you know, I kind of grew up bridging a couple of worlds. My mother was Passamaquoddy Native American, which is a northeastern tribe, and Irish. My father was Italian, so that meant I had 3 of the worst drinking cultures I could possibly have. But you know what? I don't drink. I don't touch it. So I'm an oddball. So all the way, you know, these guys know. Yeah, I know you know. Anyway, so you know, so I bridged that world, and I've spent a lot of time looking at native cultures. I spent a lot of time looking at other cultures as well to see what their version of the sky looked like. Now, it's funny when you go to get a degree in astronomy, you don't become somebody that, you know, knows every constellation, okay? Judith probably knew more than I did about constellations until I started doing our remote observatories. I always wanted to have an observatory under a really dark sky, like this. Don't tell Karen, okay? But the thing is, I put 2 of them remotely operated out in the Arizona desert. One's out in the Sonoran, about 1,600 feet, and the other one's down in Benson, 220 miles away at 3,600 feet. I run them from Connecticut, where I live. Okay, and I spent a couple of years learning how to do all the remote stuff and wrote programs to kind of do all that kind of stuff. The thing that's interesting is that when you look at the universe through different eyes, through the eyes of a telescope, the world unfolds. It's amazing how much more you can see when your eyes aren't this big anymore, the size of your pupils, about 6 millimeters, but are actually like 10 inches in diameter or more. Now, when I worked at university, I was working on a program called the parallax program, and that's the study of nearby stars and their distances. And to learn the distances to nearby stars, we use a thing called parallax. You're familiar if you put your finger out like this and you look at the wall, you see two fingers. If you close one eye, you only see one finger. If you blink your eye back and forth, your finger dances against that farther background. Well, if your finger here dancing is a nearby star and the wall background are the more distant stars, you can see that if you go some distance to one side or the other, the size of the Earth's orbit, you might see that star shift against the distant stars. And that's what I spent years measuring. And we got tens of thousands of stars cataloged as nearby stars, out to about 300 light years or so. All right. So the parallax, the whole parallax concept was how we began to learn the distances in the universe. And this is a preparation for it. It has nothing to do with my talk, actually. My talk is going to be highly technical, as you'll see. That's sort of tongue-in-cheek. It's not really, you'll see. But when we talk about the distances, we have something called the cosmological distance ladder. How do we find distances to things out there? Okay. Judith mentioned Lyra, the constellation Lyra. The star Vega that she talked about, yes, it was our North Star at one point. And the reason, as she alluded to, is that the Earth is like a wobbling top. And where it points is different places in the sky. It's a wobbling top, probably because of an ancient collision that made our axis 23.5 degrees on its side. Okay? So something caused us to go from being like this to this. And that's why we have seasons, because when we're on this side of the sun beats down right there. But when we're on the other side of the sun hits down here, it beats down here, and we're farther away. So we have a lower sun, so we have colder temperatures. Winter, spring, summer, fall. Cool stuff. But that's all elementary stuff. But when we talk about the distances to the stars and how our star plays into it, it just becomes a rabbit hole. And I started going into this rabbit hole when I was 9 years old. And when I was 9, I decided I'm going to be an astronomer when I grow up. I never wavered. I don't have a life. What can I tell you? Okay. I ended up making a space station plan. I sent it down to NASA. A NASA scientist actually looked at it and sent me back this big cardboard box. And I was like, my mother said, Mark, there's a box from NASA for you. What? I was 9. I went, gimme. And I opened it up, and there was a manila envelope with something in it. Whatever. Look what's in here. Models of spacecraft, books on astronomy and science, brochures, cloth mission patches from all the space missions we'd done. I was like, wow. And I put them all out on the floor, and I kind of tossed them up and like let them fall on me. Like, wow, it's like money, right? Like, this is my money. My currency is knowledge. And so it was so cool at age 9 to get that. And then I looked inside the manila envelope was my space station plan and a letter. The letter was from the scientist at NASA. The scientist at NASA said, you have a future in space. And he called it, back then it was the manned space program. He said, you have a future in the manned space program. Stick with this. I looked at your space station plan, and I made notations, all kinds of things that we think you're onto that are good. Really? I'm 9. Okay. And I looked at it, and yeah, he had check marks, and he wrote little comments. We're doing this now. This is cool. No, we can't have pigs and cows on a space station because, yes, I know you wanted pigs for meat, and you wanted cows for milk, but we have better ways of doing that than having animal stalls like you were thinking. So, I mean, that's what I thought, So, anyway, he ended up putting all these notations. I read them, and I absorbed them, and I decided then and there, I'm going to be an astronomer. And this guy, his name, and some of you may know him, okay, he's famous now. He works at Jet Propulsion Laboratory. He's the chief engineer for all outer space robotic missions. His name is Gentry Lee. Who's heard of this guy? See, you might not know him, but he's an unsung hero. All the rovers on Mars, Gentry Lee has his name on it. The New Horizon probe that went to Pluto and into that Kuiper Belt icy object, Gentry Lee has his name all over it. Galileo Jupiter, Cassini Saturn, Dawn probe to Vesta and Ceres, Gentry Lee has his name all over it. So this guy is freaking giant. And so what I say, and I mean this, for me to be where I am, I stood on the shoulders of giants to get there. Okay? So if someone stands on me someday, I'll be flattered. All right? I called Gentry Lee a few years ago. I hadn't talked to him since I was 9, and that was only through my space station. All right? And I said, you may not remember me. And I told him all what I just told you. And he laughed. He goes, yeah, I don't remember you, but that's the kind of thing I did when I was a young scientist at NASA. He said, how'd it work out? And I said, I'm an astronomer. He's like, yeah, that's so cool. You know, so it's like, you made it happen, dude. You know, so we try to keep in touch, you know. So that's my little astronomy story to show you how one person inspiring you can make the total difference in where your life's path takes you, you know. So that's what I did. Now, this talk is going to be a little different. It's called The Unorthodox History of the Earth. And I want to tell you, first of all, why, now as an astronomer, I'm not supposed to believe that alien life is here, correct? And the answer is yes. I'm not supposed to tell you that. I'm not supposed to think that they're here. However, I think they're here and have a reason for that. And this talk is going to actually give you some of that reasoning. Tomorrow's talk that I do, I think it's 3 o'clock I'm doing tomorrow, I think. UFOs and they're here kind of thing. I think it's at 3 o'clock tomorrow. That's going to show you in layman's terms what we in the astronomy community, the physics community, the astrophysics community now believe is the real methodology behind how UFOs go from there to here.
Ooh.
And it has to do with interdimensional travel. Now, Avi Loeb is the chair of the Harvard Astrophysics Department. I worked with him a couple times on a couple of shows, okay? Nice guy, all right? He just came out recently and said that he thinks that UFO travel does occur interdimensionally. He's joining the club, okay? And, you know, he's got a lot of credibility, but he's always hounded by the media saying, you said that alien life is coming into the solar system. No, he didn't. All he said was, we can't deny the possibility that this is alien. That's what he said. Not that they are. But the press, they jump right on and say, oh, he said it's alien. No, he didn't. You know, that's like trying to Google something, you know, and find out they give you 10 different definitions. Like Wikipedia is not always right. Yeah. Anyway, so the question about why Earth is so visible to alien life has to go back over 2 billion years. Because we look at Earth, and that's it right there, that pale blue dot, okay? And that pale blue dot, and Carl Sagan was my favorite astronomer, by the way. So he said, we are on a pale blue dot, right? Our home, our Earth. Remember, he said that. Pale blue dot was a really fascinating talk he gave, which I ate up, as you can tell. And so that pale blue dot is blue for a reason. It's blue because of oxygen. Oxygen being number 8 in the periodic table, that nasty table you saw in class in chemistry that you wanted to avoid, like the plague. I told other people this. I can sing the entire periodic table. I can. I'm not doing it. But it starts like this. There's hydrogen and helium and lithium, beryllium, carbon atoms everywhere. Nitrogen all through the air and oxygen so you can breathe it, flowing for your pretty teeth. And it goes on all the way to 118 elements. And guess what? That's actually how I memorized the periodic table, was through a song. It's very cool. It's the can, but the periodic table of the elements, okay? So oxygen being number 8, it's very interesting. It's the third most abundant element in the entire universe, oxygen. Hydrogen is number 1, helium is number 2, oxygen is number 3. You know what the fourth one is? Guess.
I would tell you.
Not carbon dioxide, that's a molecule, not an element. That hat is hurting your brain power, Seth. And you're blocking the view of everybody behind you. No, I'm very, as you can see, I'm very I'll be out amongst you. I mean, I talk like this all the time. So any guesses? What's the fourth most abundant element in the universe? Think about you. Carbon. Well done. Look, Steve got it. That's right. Well done. Yeah. MUFON guy, right? Saw the hat. Yeah. So carbon's the fourth most abundant element. And guess what? It's also the most flexible element in the entire periodic table. Who thinks there's silicon-based life? Or the possibility of silicon-based life, right? Some people do, right? Okay, let me tell you why I don't think there's silicon-based life. I am a carbon bigot. Sorry. I am. All right? You can get after me if you want, but I am a carbon bigot, and I'll tell you why. Silicon makes extremely robust bonds with anything it touches. When it bonds with oxygen, the third most abundant element in the universe, what does it make? Silicon dioxide, silicon and two oxygens. I didn't expect you to know that, but what is silicon dioxide? Sand. Yeah, but that was close because if you actually fuse sand, you get glass. Yeah, so very well done. So sand, being silicon dioxide, is a very robust particle, a very robust molecule. Very much energy has to be put into it to rip those oxygens off the silicon. And it tends to make a crystal lattice. Okay? And that's like we see in other elements like sodium chloride, which is salt. Okay, we see a crystal lattice, right? Well, anyway, you see when a silicon dioxide atom comes into the atmosphere at high speed, 90 miles up, you see a flash in the sky called a meteor. Okay? It's 90 miles away. It's the grain of sand, and you can see the light from its disassociation from 90 miles away. You need a lot of energy to split up a silicon lattice like that, silicon dioxide. So oxygen is very important to us as carbon creatures. We're based on carbon. Actually, and some of you may actually not know this, but maybe some of you do. Every single element in your body was once forged in the heart of a star. You were made at tens of millions of degrees Celsius. All right? I think that's pretty cool. You think about that. Everything we're sitting on, the stand, the water bottle, everything, the materials that make the plastic, all forged in the heart of a nuclear furnace of a star. The stars are the givers of the elements. And then those dark clouds in space that we call dark nebulae, that's where life begins. I say life began in the dark, and you can take it any way you want, but life began in the dark for real, too. The beginnings of life occurred in these dark clouds. So oxygen is very important to us. And it was about 2 billion years ago, 2.5 billion years ago, when oxygen atoms started appearing in our atmosphere, created by primitive life forms. The primitive life forms were phytoplankton. These phytoplankton were actual little tiny algae in the oceans, and then the plankton animal itself started doing photosynthesis with the sun, right? Now, when did the first photosynthesis occur? About 2.5 billion years ago. By 2 billion years ago, we ended up having a quite substantial amount of oxygen in our atmosphere. Okay, you're an alien being now. And 2 billion years ago, you look up into the sky because you've been around for millions of years before that. And you look around and you're looking for planets. You've perfected planet hunting technology. We're getting there. And you look and you find a planet that has lots of oxygen in the atmosphere. Wow. That looks interesting. What does that mean? Is that a place we can go to find life? The answer is most likely because oxygen is made by life. It's made by plankton. And when we see phytoplankton making all this oxygen, that means we, as aliens, excuse me, we as aliens might want to go there because we're carbon-based. Because remember, I'm a carbon bigot. So most likely aliens are carbon-based. Most likely aliens are also symmetric, like life form on the planet. Okay? There's radial symmetry, tulips. There's pentamerism, five-sided symmetry, like starfish. And then there's us, bilateral symmetry, the same on the left and the same on the right. That symmetry seems to be a template provided by the universe based on DNA. When DNA replicates, you've heard this, one side unzips, and a complementary side zips up. okay? Symmetry. And that's what we're talking about. So if you're a carbon-based being, you have a love affair with oxygen, guaranteed. And so this is how you're, as an alien race, we're going to find other worlds like our own. We're going to find an oxygenated planet. And we're going to go there when we have the technology. Now, the James Webb is looking for oxygen, but indirectly. Because if we look at all the light we can see, this is what we see with our eyes. Let's say from here to here. Okay? That's the visible spectrum, right? And it's red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. Okay? And that's the visible spectrum. The James Webb sees way out here. It's looking way out in the infrared, which is out here, right? Now, out in this realm, we don't see oxygen because oxygen occurs, the lines, the spectral signature is here. It's right about there. It's called a telluric line. Don't worry about that. But it's in the visible spectrum. I see them with my spectral systems when I look at it with my observatory. I can see the lines of oxygen in our atmosphere, okay? But the James Webb only sees out there. It doesn't see here. So how can it look for oxygen? Well, here's something interesting. When oxygen atoms collide with each other, they give off a far infrared signature. So based on how many of those collisions you see out there, you can infer how much oxygen is in here. All right? So it's pretty cool. So James Webb even has a place to do this, to do this search. So that's something very important. Now, we think in astronomy, first of all, I wanted to say, when you look at all the stars in the sky, even here under Bortle 2 skies, right? When you look at all the stars in the sky, these stars pale in comparison to the number of planets. We think there's more planets in the universe by far than stars in the universe. And I mean stars in the universe, that's every galaxy everywhere. More planets than all of those stars. So, what do you think the chances are that there might be life out there? In astronomy, we say it's guaranteed, all right? What are the chances of intelligent life? I mean, it's not here either, I would say. But no, the intelligent life, the guarantee isn't there. But intelligence is a potential outcome, not a guaranteed outcome, right? So a potential journey, right? So the conclusion is that we have, and now just in our galaxy alone, just in our galaxy, all right, we have maybe 10 to 20 billion other Earth-like planets in our galaxy alone of 150 billion stars. That's at the low end. Now, that's based on star counts. We might also have 400 billion stars in our galaxy. And this higher number breeds a much higher number of Earth-like planets, and that number goes to 40 billion Earth-like planets just in our galaxy. How many other galaxies are there, Mark? I'll tell you. About 2 trillion other galaxies. If I put a 1 and put the zeros behind it for all the additional galaxies there are, it would be longer than this tent. Okay? Okay, well, you have to know how big the numbers are. About that big. Okay, not that big, but about that big. Yeah, I did that calculation. I said it. I have no life. Okay? So the truth is, when we look at the universe, there's a lot of life out there. I wrote a book called The Populated Universe, and the subtext of the book is, life in the universe may be the rule, not the exception. And before we get into our next thing, I will tell you, I had a little argument with my observatory director when I was getting my degree. I said to him, his name was Art, marvelous guy, but academia, all right? You'll see what I mean. I said, Art, and I used the phrase, I think it's a populated universe. And I used that for my title of my book decades later, okay? I said, I think it's a populated universe. And he was a heavy-set guy with suspenders, look over his glasses like this at you, and he said, why, Mr. D'Antonio, what are you talking about? I went, well, and I mentioned bilateral symmetry, I mentioned carbon-based, and I'm a carbon bigot kind of thing. And he says, okay, and you could tell he was sort of just waiting for me to get lost, I could tell. And I said, yeah, and DNA seems like a template that the Earth automatically makes. We know that the building blocks of life have been delivered by comets and meteors and asteroids to our planet. We know that. We also know that the Earth makes them itself. The Miller-Urey experiment in the 50s showed that amino acids, building blocks of life, are made automatically just because of lightning striking the primitive atmosphere, right? So I think that life is a template that the universe provides. It might be a universe of life. And he looks at me. He's passed on now, okay, so he can't hurt me. He might, I don't know. It's just, we need to go into that realm. Okay, he looks over his glass, he goes, are you finished, Mr. D'Antonio? I'm like, yes, Art, but do you understand? And he goes, get back in the observatory, he said, and leave Captain Kirk to us.
Yeah.
And I went, I will. Scotty, beam me up. So I ended up going back and we smiled. And now that was 1983. That's when I got my degree. Okay, yes, I'm old. And I went back in 1988. Okay, 5 years later, hadn't talked to him in all that time. The first planet confirmed around another star was found. Okay, I walk into the observatory, open the door, same smell. You could smell the books in the old library that guided me all through getting my degree. I walked across the creaky wooden floors. The noise echoed throughout the whole building. It didn't have any fabric on the walls. It was just the hard walls. You could hear the echo. You could hear people sniffing in other rooms. It was such that kind of a building. And I walk into Art's office in the alcove, and he's on his phone bellowing. You hear his voice throughout the whole building. Okay, and I go to his office, and I'm debating, should I kind of just poke my head in? So I decided that's what I'll do. So I poked my head in, and I smiled. He's on the phone. I hadn't talked to him in 5 years. He goes like this. Remember we talked to each other through those lovely U-shaped scoops called the telephone? Yeah. Okay, well, that's what he was using. Okay, he covers up the mouthpiece, and he goes, it was only one planet. I lived rent-free in that guy's head for at least 5 years. That was the coolest thing. And I said, it's just the beginning, Art. It's just the beginning. And he goes, ah. And after that, I mean, he passed away. Not there, okay, but a couple years later, he passed away, and I never got to, go back and give it to him again, okay? But that's okay. But you see the point, okay? When you look at the university world and academia, they tend to be kind of narrow. Right? I'll give you an example, and then we'll go on. Neil deGrasse Tyson had said a few years ago, he said, when asked if there was alien life, he said, well, no, I don't believe they could be here. It's just a vast universe that's so big, there's no way for them to get here. And so, no, I don't believe they're here. That was his response. Well, then I got a LinkedIn request from Neil deGrasse Tyson, and I ignored it for 3 months because I didn't think it was him. And I went into it, said, let me just get rid of this one. I get in there, it was him. So I accepted it. And I think that he follows not just me, but other people. Now, some years after, he's asked the same question again, and guess what he says? Well, I just think we need more data. That's not the answer he gave before. I judge that as a win. We're taking arrogant academia and we're kind of dragging them forward into the real world, right? I think that's pretty cool, don't you? Yeah, I agree. So now, yes, we don't know that there's life elsewhere, or do we? Now, we are looking for it everywhere we look, and every single NASA mission to the outer planets has, as one of its tenets, to find evidence for past or present life, Mars especially. I think there's life on Mars, but I think it's buried under the South Pole. Deep in the water aquifer that runs under the South Pole is a briny aquifer down there. And I think that actually, am I still good? Yeah, I think that actually is a location where there might be microbial life. Now, there's a mission on the way to Europa right now, which is Jupiter's moon. It's 2,000 miles across. I see heads nodding, they know. Okay, and it's got an icy mantle that's fairly thick. Now, the moon is, again, just about 2,000 miles across, to the size of our moon, right? Has a thick crust of ice, and underneath it is an ocean that goes down 90 miles or more. And that ocean looks like an ocean that might actually be warm enough and suitable for life. Why would we look in the darkness for potential life? The answer is we would look in the darkness because we found life in the darkness here. The hydrothermal vents at the mid-Pacific Ridge on the Wadden Fuca Ridge off Oregon. Okay, we found that there's life around those black smokers. All right, I've worked with folks at Woods Hole Oceanographic Institution. I have a little piece of a black smoker, which I cherish. It came from 4,000 meters under the ocean. Oh, look at this little piece. This is cool. Mine. Okay, the neatest thing, because it represents a tremendous leap in knowledge and understanding. And so this thing, these black smokers spew this mineral-laden water that bacteria flourish with and enjoy and eat, and these little oases form, right? Well, they're on Europa too. And Europa has geysers that reach the surface and spew into space. Water and carbon and other organic molecules. I think it's not too much of a leap to think there might be life under that ocean or in that ocean. And so that's what the Europa Clipper mission is designed for, and it's on its way. It'll be there in a couple of years. It's going to take a while to get to Jupiter, pretty far away, over 5 astronomical units. An astronomical unit's 93 million miles. You know how that goes. So here in our solar system, we're looking for life. And we're going to be looking for life using the light coming from faint planets around other stars, right? Now, understanding where life comes from, we have to consider how it started here. To understand where in the stages of the formation of a planet, you might find clues that life could develop there. And to do that, I brought a high-tech device. All right, we only know about life here on Earth, but the fact is, I'm pretty sure that at the end of this, you'll have a better feeling for the scale of life on the planet. All right, and I think this is something that you'll enjoy. So without further ado, the technical piece of apparatus I brought is a roll of toilet paper.
How much money is it?
Oh, it's used. Oh, wait, no, I don't mean that. Not that way. I've used this many times before. It's actually not toilet paper. It's the crepe paper backing for wallpaper. And I spent 6 hours drawing every 4 inches lines for the locations of all the perforations that you would get in toilet paper. And so it really implies correctly that I don't have a life. And I'm okay with it because I'm sure that after this is done, you'll agree, right? But I want to just show you, let me just get this little disc in here, right? Here's what we're going to do. I'm actually going to go around out amongst you, the rabble-rousers. I mean, you're raising so much ruckus out there. And we're going to start by looking at the history. Each one of these sheets is 14 million years long. Don't worry, we're not going to do any math. But you're going to see it's visual, and it shows you where life began on the planet and when, and how much time passed between things that were going on the planet. So I'm going to ask Seth Feinstein to come up here with that big old brim hat of his. Thank you. And stand right there, right here, actually. And you're important, though, because you, sir, you're where life and the Earth forms. See, it says Earth forms from the solar nebula. Seth Feinstein, everybody. He's a bringer of life. So, as we move along, you'll notice that right away something else is happening, and that's the formation of the moon. And if you notice, that happened 4.6 billion years ago. This happened 4.5 billion years ago. Now, the formation of the moon is a bit of we're in a bit of a quandary. We're not really sure how it happened. We think it was a collision with a Mars-sized object, and that could be true, all right? So now I'm going to come around now, and as we go here, we come back, and the next step here, the oldest Earth rocks were about 4.4 billion years ago. Remember, 14 million years per sheet, right? And so the Earth is now percolating, it's going, and all of a sudden here, the atmosphere 4.2 billion years ago starts to form. Now, where did the atmosphere come from? Well, you guys should probably have an idea where the atmosphere came from. Just go ahead and yell it out. Excellent. That's right, volcanoes. I got an answer for everything, I'm sorry. Yeah, but yes, volcanoes started spewing gases, and those became the primordial atmosphere. Those are mostly carbon monoxide, carbon dioxide, methane. There was some hydrogen. Okay, Notice the absence of oxygen. Okay, there was no real oxygen yet. All right, and that kept going. I'm sorry, you're going to want to fall, And as we move through here, okay, let's see if we can give Judy anything here, Judith. Let's see if we can give you something. I'm afraid you're going to be in a blank area. You're in an area where not much was happening. I hope you're okay with that. Okay.
Just stuck to going on with the blank area. Yeah. So I'm okay with it.
All right. So you notice how much blank is happening. This is 14 million years of what appears to be nothing, except back there we have the formation of the early atmosphere happening, right? And that started. So for over 14 million years, there's a clip in every sheet. We had the atmosphere building up and building up and building up and building up until all of a sudden we get here. Now we're looking at 2.5 billion years ago out here, okay, at the edge of the tent. And then 2.5 billion years ago, that's where the early cyanobacteria, those plankton that make oxygen, started to show up 2.5 billion years ago. Look at all the time that passed before oxygen started being made by small microbial life on our planet. That's pretty cool. Judith, you don't have to hold your arm up if it gets tired. You can, yeah, there you go. You relax, all right? I'm the one that doesn't have to relax. So now, that's building up over there. It keeps going and going and going, all right? Thanks, Trey. Oh, thank you. Yeah, thank you. And so we keep going, and Carrie's wife is kind enough to help us there. Thank you. And so now all this time, oxygen is building up in our atmosphere. All this time. And it keeps, you really can't say I don't have a life. I had to draw all these lines and number all these sheets. There's 300 of them. Oh, yeah, it was just no fun. But I knew, and see, you're going to get it now. Yeah. Oh, lucky you. You got a good, yes, 2.7 billion years ago, all right, she got the buildup of the early oxygen atmosphere. Now this, yeah, I can tell by the look on your face. So that means now, this is at the, you gonna live? Okay, just making sure. You need oxygen? You got some right there. Okay, so the bottom line here, well, for you, I know the bottom line is oxygen, okay? Okay, now here's what happened. See, in that time where oxygen built up, it turned out that over a very short amount of time, we had something called the Great Oxidation Event. We had more oxygen growing up and populating our atmosphere than we thought. And it happened rapidly. Now, you're an alien race, and you're a multi-million-year-old race, and you've got records, and you say, let's go look at that planet thing that we saw, that other planet. And you discover, hey, their oxygen level just climbed astronomically over the last million years. This is incredible. There must be something there. It must be life. Now, why would they say it has to be life? What do you know about oxygen and how it reacts with rocks and other things? It reacts with iron, doesn't it? And what's it create when you combine oxygen with iron? Rust. Yes. How many know that's why Mars is red? That's why Mars is red. It rusted. When its magnetic field died out early in its evolution, the magnetic field died, and thus the ultraviolet radiation could strike the water molecules in the atmosphere, separating them into hydrogen, which drifted away, and oxygen, which had nowhere to go but down, where it combined with the iron compounds in the crust, making a molecule we call hematite, which is rust. That's Fe2O3 to the chemists out there, all right? And so this oxygen then was lost from the Martian atmosphere, and it created exactly what we see, a reddish surface coloring on Mars. The real coloring of Mars is dark brown, and you can see it when you wipe away that real thin surface layer that's as thin as talcum powder on the surface all over the whole planet. And by the way, Mars' atmosphere is so thin that the talcum powder surface takes a wind of several hundred miles an hour to actually dislodge it and blow it into the air. That's how thin the atmosphere is on Mars. So you wouldn't even feel a 300-mile-an-hour wind on Mars. You might feel or hear it. Nice little, that's it, you know? All right, so we have the oxygen buildup in the atmosphere, and then back here, okay, this was at 2.5 billion years ago, we ended up with the Proterozoic era, the earlier life, okay? So that's when the first life started to show up. And it was really life that kind of lasted a long time, as you can tell. It keeps going and going and going. It lasted throughout all this time. Uh-oh, don't want to, right? So all the way from oxygen over there. Yeah, she hasn't gotten over that, as you can tell, right? Yeah. You should be embarrassed. You're a bad oxygen example. Look at you over there trying to hold that thing up. I've known her for a long time, so it's okay. So coming through here, we keep going. And now, as we get down here, all right, we move through a lot of blank spots. Again, 14 million years per square. And now we get to here. And well, look at this. We have the first supercontinent on the planet. It was sort of an ocean world at that for much of the time, but then we ended up getting low spots being populated. It rained. Okay, so when we had, oh, thank you guys for holding that. And all this time after the oxygen buildup, our atmosphere was 90 times denser than it is now. That's what Venus' atmosphere is now, 90 times the density of ours. Venus being so close to the sun, however, means that it couldn't rain. It was too hot. So Venus never could release that extra 90 times the density. It couldn't release that density. So that left us with a planet perpetually in the greenhouse zone, Venus, and left the temperature on the surface at 900 Fahrenheit, all right, perpetually, all right? Earth could rain, and it rained for millions and millions and millions and millions of years. Weather reports were easy back then. More rain in the forecast tonight, Frank. Yeah, and that went on for millions of years, okay? So now, thank you. Sorry that you've got nothing, you guys, in the middle here. But you are, you know what? You're raining. You're raining here. You're raining lots and lots of rain, okay? And, like kind of like how it was here today. I heard that was quite a storm, huh? All right, so now we come down here, and the roll's getting smaller again. A lot of nothing going on here, and I'm going to come around here, all right? And then it keeps on going and keeps on going, and don't worry, I'm not going to run you over. All right, and as we come down here, we notice something else. This is where the earliest continent of Rodinia actually began to break up. Now, why did the supercontinent, why did it break up? Who knows the answer? Why did we had one big continent, and it started to crack apart and move around? What was causing that? Do you know what? Yes, thank you. The shifting of the tectonic plates, the plates that are the thin crust on a molten interior that we stand on and live on every day. Some people can't handle the fact that just a few miles beneath their feet, it's molten magma for thousands of miles. Yeah, that's true. At Yellowstone, if you go to Yellowstone, it's 2 miles beneath your feet. Okay, not 40 and not 70, not 30, but 2. That's why the geysers, you know? So this is where it broke up. It was 800 million years ago, right? And then if we keep coming around here, we'll notice now things start to happen. Early multicellular organisms. Wait a minute, Mark. Does that mean that it was all one-celled organism? Yes, it does. Multicellular occurred 700 million years ago. More than one cell. That's really interesting considering that we had life way back 2.5 billion years ago, but that's single cell creatures. All right? These are multicellulars now. And as you see, a lot of time passes, but now things are starting to happen faster. What's going on? Well, this is called the Precambrian era. It was like the Cambrian era, like 500 million years ago or so. And around 500 million years ago, that's when the first organisms showed up that actually had shells. So clams and things like that showed up about 500 million years ago. Shells are interesting. They're calcium carbonate. They're a structure that developed out of an evolutionary mistake, a mutation. And it turned out that it was favored for continuance. So shelled organisms continued.
Unshelled organisms.
At a certain point, did not. All right? And some did, obviously, when they got bigger. And then 510 million years ago, the Cambrian period ends, and we reached another one called the Ordovician period. Why do I put it there? Because around 490 million years ago, we started to see the first fish. So a lot was going on in the early Earth, but notice we went from multicellular organisms to fish pretty quickly. That's pretty incredible to go that fast. This is called the explosion of life. And so far, we haven't had any events that wiped out life on our planet yet, so far. So we went very quickly from multicellular creatures to early fish 490 million years ago. We're cranking, guys. But then, dang it, we had an extinction. We lost 86% of all the species on the planet, and that was at around, 440 million years ago, all right? So this was the first extinction event. There were 5 major extinction events on the planet, and 440 million years ago was one. 86% of all life died. Luckily, sorry, man, luckily, we didn't have to wait long, because after that extinction event, and they died, okay, right here, right, 408 million years ago started the Silurian period. Now, I put the periods on here because that's when certain life forms appeared. And that was 400 million years ago, we got the first insects that appeared on our planet, the first insects, okay? That's pretty cool. Now, at this point, we had another extinction that happened at around 340 million years ago, extinction number 2, the Devonian extinction. Now, what happened there? We lost about 75% of all life on the planet went extinct. Now, when something goes extinct, what happens? Well, it's a creature, a family of creatures with a whole ancestry that populates a certain niche, all right, an ecosystem niche, and they dominate it, all right? Well, when they die out through some reason over a period of centuries or whatever, now it's an open niche, and something else is going to rush right in there to fill it, and that's what happens when we have extinction events. So we had an extinction event here, and at 340 million years ago when that happened, what rushed in to fill the gap were early reptiles, creatures that would be, like early dinosaurs. But they weren't dinosaurs. They were just reptiles. Now, we stop here for a moment and say, about 280 million years ago, this is when the continent of Pangaea, the supercontinent of Pangaea, was fully formed, all right? And then shortly thereafter, we have the Permian period begins. The Permian period goes all the way, okay, to 252 million years ago. And at that point, the third major extinction event occurs. And we end up with the loss of the biggest number of creatures on our planet we've ever had, and that's 96% of all life died. All those niches were killed and emptied. Back there, we saw the first early reptiles, right? And they eked out a living. But during the Permian period, guess what happened? The creatures that would become mammals, like us, were dominant during this Permian period. And when they died in the Permian extinction, something rushed in to fill the gap. And you know what that was? Dinosaurs. Good girl, Katie. Well done. Yes, dinosaurs rushed in to fill the gap. And thus began the age of the dinosaurs. And they lasted all the way until 65 billion years ago, didn't they? All right, so when we look here, this was 252 million years ago where we lost 96%. And then we had another extinction event, and that was at around 208 million years ago. And this one wasn't an extinction event more than what we call a biodiversity failure. If you look at an ancestry of creatures, you have one ancestor creature and you see this radial spokes coming off of it, of all these other creatures that formed from it, right? That became descendants of it. Well, those creatures, all right, those in many ways, those many spokes provide many avenues to potential success. Well, most of those spokes didn't exist for some reason or another And that's what's called a biodiversity failure. So that's another extinction event, all right? And that's 4 extinction events we've had on the planet, right? And now, just as an aside, 200 million years ago, that's when the Atlantic Ocean opened up. First time, all right? And now the other thing that's interesting is that 180 million years ago, we had early birds and mammals. That's interesting. So now, in spite of the fact that the dinosaurs have taken over the life here, okay, and become the major life form, we still had other things happening. It doesn't happen in a vacuum. It doesn't stop. And just take a moment to look around the room and see how big this thing is. It's 117 feet long, all right? And it took us all the way to 180 million years ago to get the first early birds and tiny little mammals on our planet, okay? So we're talking 4.56 billion years of time had to pass, and the planet had to develop for that time. So this should give you a clue that any planet that's going to have life, if it doesn't have any extinction events, then maybe life could have formed a little further back. But with extinction events, it stops life and it restarts, stops life and it restarts. But guess what? It restarts. It's always restarting. And that's the thing about the universe. It seems to provide a template for continuance of life, even in the face of extinction. And that's amazing. So now we move forward, and we have the first 150 million years ago, early flowering plants. Now remember I talked about early insects back there? And it took a few more million years before we started seeing flowering plants. You know the connection between flowering plants and insects, of course. Pollinators. And plants developed the capability for insects that existed before to literally make use of the insects to spread the plants around the globe, around the world. It's not a flat earth, it's a globe, and you know that. Trust me, I argue with that, but you can't believe how many people argue with that. All right, so now you'll notice the writing gets fast and furious here, and that's because of the nature of what happens next. Here on our planet now, okay, we had the first pollinators, or the first plants to show up so they can be pollinated, again, 150 million years ago. 80 million years ago, the Rocky Mountains formed. So this region was formed 80 million years ago. Collision of tectonic plates, slow motion, okay? And now, it was now at 65 million years ago, where we had something called the Cretaceous Paleogene boundary, the Yucatan event, the Chicxulub impactor event. You know it as the extinction of the dinosaurs, all right? The extinction of the dinosaurs occurred 65 million years ago. It didn't happen all at once. See, that's the thing. People think, boom, an asteroid hit and all life was extinguished like that. No, that's not what happened. It was a gradual thing, and the Earth reacts slowly to impacts. So when the impact hit, a cloud of dust went up into the atmosphere. And that cloud of dust blocked sunlight. That sunlight being blocked meant that plants couldn't survive. And plants began to wither and die over periods of months. And when that happened, the creatures that ate the plants, the herbivores, dinosaurs, they died. And when they died, the creatures that ate the plant eaters, the herbivores, they died. The raptors, right, and the Tyrannosaurus rexes of the planet at the time, and then they all died. So it was a domino effect, right? And that extinction killed 76% of all life on the planet. We had plenty of life in the water and plenty of life on the land, but that was 76% of it. And this represents the last major extinction event on our planet. So we had 5 major extinction events, all right? So now, all right, we get to here, and this is the end. And I'm gonna do this right now. All right, so now, I want you to notice something. First of all, I'll get to it in a minute. And it was 40 million years ago, right here, this line. This is when India collided with Asia. The Indian tectonic plate collided with the Asian plate. And guess what the result was? Right, Himalayan mountains, Mount Everest, as a result of this slow motion collision between continental plates, all right? That's amazing, right? Now, The other thing is very interesting. During that time, this is when we actually started to have global cooling on our planet. We entered an ice age at that point. Now, why? Well, it could be because of solar energy impinging on the planet was less for some reason. The young sun had already, begun to go past its young, tumultuous days and started to level out into a steady beam, for us. And that ended up causing potentially a cooling, all right? We don't really know. But then 23 million years ago, again, something that you might find odd, 23 million years ago was the time where we actually had the first ice at the poles. We never had ice at our poles before until 23 million years ago. All right, so for the entire time of our development, all the way to Seth, with a cowboy hat. Okay, he's been standing there dutifully the whole time, daydreaming, humming to himself, and they appreciate him doing that. Thank you. But in all that time, we never had ice at our poles until here. Okay, so this line here at the end represents us here in this tent tonight. And this is where we had ice at the poles for the first time. It's recent. It only just happened. It's not normal for our planet to have ice at the poles. Just look at the history. First time, 23 million years ago. And by the way, when we look at this ice, the first Antarctic glacier was about let's say from this I'm looking. We're looking at only about 10 million years ago when we had the first Antarctic glacier ice. Okay, so the first ice at the poles began to show up 23 million years ago, and about 10 million years ago, we had the first Antarctic solid permanent glacier. Okay, now another thing to notice here is that there's another line next to this line, which is so hard to see. Okay, it's about that far apart. That's Lucy, Australopithecus afarensis, our common ancestor. That's where Lucy is on this entire scale. Was just yesterday, not even earlier today. Isn't that cool? Also, here's where dinosaurs died. And here's today. Dinosaurs are a recent event, recent extinction. That's recent history, not ancient history. Just look at the development of the whole planet. Dinosaurs are 18 inches from today. Actually, 13 inches from today. All right? On a scale of 117 feet. Give you a better perspective on the evolution of life on a planet? Put yourself in an alien's shoes now. Aliens look at the life, and they look at oxygen in our atmosphere over there, all right? I forget your name.
Nate.
Oh yeah, Nate, right, you got the night vision, thank you. Make sure you talk to Nate about that if we get some clarity. So Nate's holding a relatively inconspicuous location in our Earth's history, but oxygen was building up. If you're an alien race, and let's say you looked at Earth there, you'd say, well, look, there's some microbial life, right? That's cool. Okay, multicellular, well, that's millions of years to come. So this multicellular life they'd see. Let's say they look back there, way back there in the corner with our laughing girl back there. Yeah, I know. She's funny. Sandy's funny. Okay, so you look at where the oxygen first starts building up, and let's say that they looked at the planet there. They'd see a planet with oxygen building up in the atmosphere. That's cool. They'd say, hey, I don't see life yet, but oxygen building up, that means there's maybe these single-celled creatures out there. There might be life. Now, oxygen on its own doesn't necessarily mean anything. It's the continuation of oxygen in an atmosphere that means the most. Because oxygen loves to dive into the ground and bond with everything else, like at Mars. But it does that here too. Way more. Thousands of times more than at Mars. So why do we still have oxygen? Because we're making it thousands of times faster than Mars. All right? So we have oxygen in our atmosphere that's being replenished, and that's the key. An alien race would notice by looking at our planet over time, hey, that oxygen level is actually climbing. Okay, oxygen gets to 21% here, but back in the Permian it was at 33%, and then it diminished. Okay, so clearly oxygen has been depleting over time. trying to find a balance. I have records of all the elements and chemicals in our atmosphere going back all the way to the Cambrian era, 500 million years ago. Carbon dioxide looks like this. Okay. Oxygen looks like this. Okay. Other compounds look like this, There's rises, there's falls, there's cycles. All right. So when people say we're putting too much carbon dioxide in the air, yeah, we have something to worry about there. We're responsible for a piece of it, yes. But when you look at the global picture, carbon dioxide's been doing this for millions and millions of years, going up and going down, going up and going down. If you have a lot of volcanic eruptions, you get a lot of carbon dioxide and methane. Methane's a greenhouse gas. That greenhouse gas causes this greenhouse effect, which blocks things, which causes all kinds of problems, which causes the CO2 to rise, etc. And thus we have more carbon dioxide. We have less volcanic eruptions, we don't get as much, right? So the bottom line is that we have cycles on our planet, and we're just infants in trying to understand our own world, and here we are going to try and find other worlds, right? Right? So, yeah, but we're doing it because we're curious. We're a curious race. And the other thing that I'll say, closing, is that as a curious race, one of the things that's most important to understand about us is that every life form on this planet, every life form shows curiosity. It's a characteristic. Yeah,
It's a chair.
Would you like it? You want a chair?
I think so.
Curiosity is a characteristic of every life form on this planet. And that means that maybe that's also a template in the universe. Curiosity built in based on DNA, based on replication, based on bilateral symmetry and symmetry of all kinds. I think that's pretty interesting. So there's a lot of templates that the universe may be providing to foster life in our universe and on our planet. This process, everything we've just done here by toilet papering my audience, which I think is great, okay, tells me that we, being a primitive race, we have the ability to move out into the universe if we can just get a little bit more technology. Because I'm convinced the others who've already been here and done that are already here. And tomorrow, I'll show you how they got here. Thank you, guys. If you have questions, let me know. If I have time, I'll answer them while I'm re-rolling my toilet paper. Yes.
What do you make of that interstellar object? I believe Oslo is saying that it's a extraterrestrial race.
Yeah. Avi actually didn't say that. He didn't actually say that, but okay, that's a good example of how the news makes you think that he said it. He didn't say that, but I can explain. I took a picture of it with our observatory.
What do you think it is?
I think it's an interstellar comet. And the reason I do is because it exhibits cometary properties. It has this diffusion of material falling behind it. Some of the components look like carbon dioxide and water ice like we expect on comets. A lot of water, actually. So this is a pretty good sized object. It's between 350 feet and 1,000 feet.
Don't hit us.
No, it's not. It's going to be millions of miles from us, so it's not going to ever hit us. Yeah. And it's called 3-Eye Atlas. The first one was 1-eye, eye meaning interstellar, and that was Oumuamua. Okay. And the press got that wrong, too. They said that Oumuamua was a flat, or a spindle, long and thin. It was actually a pancake shape. All right, a pancake. It was flat. All right, like flattened dough. All right. And you had a question over there?
Now, do you think we could terraform Mars?
Oh, you know what? I did a talk on terraforming Mars, and I think we can do it. And there's a reason, and that's because we have to be able to get Mars' magnetic field working again. Well, we're not going to be able to get the magnetic field working again, but we can fake it. We can actually envelop Mars in an artificial. I'm sorry, guys. You're getting this in your faces. We can actually create a magnetic field between Mars and the sun, and the solar wind will push that magnetic field and drape it over Mars, protecting Mars. And that process is actually something that's already in the NASA docket for exploration. Yeah, and so if we can terraform Mars, the first thing that will happen will be that we will see an increase in clouds on Mars of substantial density. And we'll see an increase in Martian surface pressure because the oxygen in the atmosphere and the water molecules isn't going to get disassociated by this ultraviolet radiation hitting it because the magnetic field will protect that Martian environment from that. So yeah, of course. I'll be here tomorrow for all those questions too if you want more. Yeah, you had one?
Yes, does Apophis help circles drive?
No, Apophis, okay, let me explain. When we have these asteroids that are coming toward us, one of the problems that we have is that we don't know their coordinates, we don't know their orbits yet. Okay, 3I Atlas, this latest interstellar object, we didn't know. So that got a lot of scrutiny. And when you see an object you don't understand, you put it on something called the Sentry List. The Sentry List, maintained by many different stations around the planet, is used to study objects of a nature we don't understand to try and get their orbits. And if we can get their orbits, we can decide if they're going to be a threat to us. In the case of Apophis, it was on the Sentry List. Thanks for doing that, Nate. I'll just roll this. I'll do this way. Yeah. And Apophis was on the Sentry List, but then it was taken off after we were able to establish its orbit. And they realized, oh, okay, Apophis isn't going to hurt us at all. All right. I will definitely be streaming Apophis going by when it happens, you know.
Just and yeah.
Other questions? Yeah, way in the back. Oh, that Trey?
Yeah.
Oh, yeah.
So, sink your toilet paper down,
Yes.
reach the end of the roll of your toilet paper that the earth gets wiped out.
Boompa. I'm glad you got a chance to use that joke. You said it the other day. That's Trey Hudson, by the way, one of your speakers.
Yeah, thank you.